Hi, so these are our notes for complex identities. It's our last little set of notes for our Unit 2A, Part 1. So you guys can go to your table of contents right there, highlighted slide 24 and 25 is complex identity. So you can pause here so you can write that down. So you guys should go ahead on over to slide 24. We're going to do like a little mini review about complex numbers and then talk about the identities. There's two of them, but we'll talk about how they're the same thing. So complex numbers, there's two parts. That's why they're complex. There's a real portion. That's your A term. And then there's an imaginary portion. That's your BI term. So the part that has an I, that's imaginary. So here's a little table over here. It just shows you I to the power of 1 is equal to I, but I squared is equal to -1. So if you guys recall that I is equal to the square root of -1. So when you square a negative, or when you square a square root, they cancel. So I squared is just equal to -1. When you take I cubed, though, it's actually equal to -I, and I to the fourth is +1, because if you have I squared times I squared is I to the fourth, and -1 times -1 is +1. So that's kind of the reason behind all this. Okay, so here's our little review of operations, adding and subtracting. When you type in your answers, you'll just go into these little text boxes. Mine are just handwritten. But what you're going to do is go ahead and your how-to for adding and subtracting is just combine real with real, and imaginary with imaginary. And you guys can change the text box or text size to fit better in your little text box. Okay, so when I add real with real, I add my 3 and my 2 and I get 5. And then I add my imaginary, I add 5i minus 3i and I get 2i. And that's my answer, 5 plus 2i. If there was a minus sign in between, I would have distributed that first and then just combined real with real, imaginary with imaginary. Okay, multiplying, I'm going to have some more work shown here that you guys won't really have on your paper, but what you have to do with multiplying is you use box method. And replace I squared with -1. So I'm going to show my work kind of up here on the top. You guys aren't really going to have the work shown. You're just going to have your answer written down, but this is just review. So we're multiplying this right here, this 3 plus 5i times 2 minus 3i. So on top I have 3 plus 5i. On the side I have 2 minus 3i. When I fill in my boxes, it's just like a multiplication chart. So 2 times 3 is 6. 2 times 5i is 10i. 3 times -3i is -9i, and 5i times -3 is -15i squared. So what we're going to have here is we're going to have real and we're going to have imaginary, okay? So there's no I squareds. This is over here. I squared should never be left in your answer. It should always be replaced with a -1. So I'm going to replace my I squared with -1. So this is -15 times -1. So this whole thing's going to end up just being +15. So basically whatever was in front of your I squared is going to be the opposite sign. So I'm going to add real with real, imaginary with imaginary. So 6 and +15 gives me 21. And then 10i minus 9i gives me I. So I get 21 plus I. So that's just our little review about complex numbers. Okay, so just complex numbers, a little review of that. Okay, so what's new, because you do that in math too, what's new is the identities to multiply and factor. Okay, so you'll just fill in where those little lines are. So the multiplying is if you are multiplying out A plus BI times A minus BI. So these are what we call conjugates. They look exactly the same, but one has a plus, one has a minus. Instead of doing box method like we did over here for the other example, all you have to do is take your A term and square it, take your B term, square it, and then add them together. That's what this says right here, A squared plus B squared. So if you have conjugates, complex conjugates, where they look exactly the same, one's plus, one's minus, all you have to do is square your A, square your B, and you're done. So let's go do an example of this. So you guys are going to go to page, I believe it's 49. I think it's 49 in your guys' workbook, and we're going to do some examples of this. Okay, so it says determine whether an identity can be used to rewrite the expression. So what they want you to do here is you're just double checking, are these complex conjugates? Okay, so it says 10 plus 7i, 10 minus 7i. Do they look exactly the same? Do they have a plus sign in between? Yes, check. We're going to say yes, we can do it. And so the way that it works is all you have to do is square A and square B and add them together. So you just have to identify what your A is. A is your real piece. B is the number in front of your imaginary piece. So A in this problem is 10. So we're going to take 10 and square it. B is not with the I. B is just whatever number is in front of your I. So it's 7, and we're going to square that. So 10 squared is 100, 7 squared is 49, and we get 149. So instead of having to do box method, we were able to just go ahead and take A, square it, take B, square it, add them together. That's it. Okay, we're going to do one more example of this. On the back side of that paper, we're going to do number 3. So again, you have to decide, can you use the conjugates? So yes, we can, because they look exactly the same, except for one has a plus, one has a minus. So what you have to do is identify like your A and your B. So my A for this piece is actually 8x. So you didn't include the I when we did the other problem for B, but you are including the x. That is part of the real portion. So my A is 8x, my B is 15. So you're going to square A, which is 8x. You're going to square B, which is 15, and then you're going to add them together. Okay, so you take A, which is 8x, B, which is 15, square them both, add them together. So I put the 8x squared in parentheses to remind you that you have to distribute it. When you square something, you multiply by itself. So 8x times 8x is 64x squared. And then 15 times 15 is 225. You can't combine those together. One is has a variable, and the other one is a constant. So on this problem over here, they were both just numbers. 149, we added them together. Here we had a variable, so they weren't like terms. We couldn't actually add them together. Okay, so pretty easy. So what I want you guys to do is pause the video, and I want you to go do numbers 1, 2, 3, and 6 on page 53. That was like our classwork assignment. So pause right now, go do those 4 problems, square A, square B, add them together. Okay, and then once you're done, we're going to go back and do this factoring the opposite way. Okay, so this identity is the same identity, basically just going backwards. Instead of being asking you to multiply, it's asking you to factor. And factoring, remember, is breaking down into multiplication of 2 smaller things. So factoring and multiplying are like inverse operations. So what you're going to do is look at this thing called the sum of squares, and it can only be factored with complex numbers. When you factor it, you take the square root of each piece, and you have A, when you take the square root, and then take the square of the second piece, you get B, but one gets a plus and one gets a minus. What's different is that you actually have an I here. So unlike yesterday, when we had the difference of 2 squares, it was a difference, it was a minus sign, you didn't need the I. But the sum of squares has to be complex, it has to have an I. So it's exactly what we used on that other one over there. Okay, so there's only one example of this in our little notes, but the way that you factor it is just like the difference of 2 squares, except for you have to add an I on your B piece. Okay, so let's go do our one example of this. So example 2 on page, I guess 49, I said. All right, so it is a sum of squares. So it has a sum, and both of these numbers are what we call perfect squares. Okay, so what we have to do is we have to take the square root of each piece, so the square root of 9x squared and the square root of 169. The square root of 9x squared is 3x because the square root of 9 is 3, the square root of x squared is x, and the square root of 169 is 13. Okay, so you square root each piece. All right, so when you put them together in the parenthesis, you have 3x plus 13i and 3x minus 13i. So you take the 3x that goes into the front of both of them. Use my highlighter. The 3x goes into the front of both of them. The 13 gets the I attached to it, and then one gets a plus, one gets a minus. Okay, so whatever they are, you square root the first piece, square root the second piece. The second piece gets an I attached to it, and then one gets a plus and one gets a minus. So it's a lot like what we did yesterday with difference of two squares, but if there's a plus sign in between, you have to put the I on the second piece. Okay, what you're going to do now is go do the other examples, or other classwork problems. Numbers 4, 5, and 6 are the factoring problems where you're going to go ahead and square root, and then the second piece gets that I attached to it. After that, you need to put, what was it, page 49 over here and page 50 over here on slide 25. And then we did some practice quizzes of a bunch of factoring problems before our quiz. Okay, that's it.